Yeah, sure.
So, Tarmo's not talked about generalizations of state, called stacks.
Yes, exactly. So this is an exercise about effects in algebraic theories, if you wish. Thanks very much for the introduction and intuition. So I think I can rely on that quite a bit in this talk. So it's joint work with Danel Ahman, who is a student at Edinburgh. I'm from Tallinn. What is it about? What is an effect?
This is.
I don't think it's a very good question in the sense that, but the answer is, well, is largely our decision, right? It depends on what we want to see and what we want to refuse to see. So there is a spectrum of impurity. I mean, what is kosher for someone isn't for other people. It really is like that. And I want to show this on the example of computing with a stack, looking at three different sort of, the notion is an overused word, but three different kinds of flavors of effect that you may want to track, or detect, or observe in computing with a stack. I'll do very little in the talk. I'll just show you three different monads for computing with a stack. And actually also the corresponding algebraic theories. You can think of what the right Haskell primitives, for example, would be, depending on how you're doing it. I'll also speak about equations. Equations are very important for me. I don't, for the moment, care too much about the language design for this, but what matters in theory. So, yeah, a stack is a kind of a store with a specific interface, right? But as the first thing, you could just think of it as an instance of the universal idea of a store, where you can observe what the contents is, you can overwrite it, so you can change the contents of the store to some new contents of the store. So, of course, stackful computations, we should be able to capture them in the state monad for for what is in a stack, which is just a list of elements, right? So you could, in principle, describe the dependence of the final stack contents on the initial stack contents. That's it. That is the effect of your stack computation in the end of the day. Well, the initial stack contents was depended on somehow, new contents came out. But of course, a stack is a specific kind of a store, so I could work with a monad that tracks net write effects of stack computations. To also try to be more precise and work with a monad tracking also net read effects. So I'd like to see in my notion of computation how deep actually I went into a stack. And if I didn't go very deep, then really what was below where I went was irrelevant for the computation. There could have been a deeper stack with different. So let's get going. So this is my stack monad version 0, the state monad. I want to work with a stack of elements drawn from a set E. I just use the state monad for the set of states S, which is just list over E. Everyone has seen this. It's nothing to command. This is the monad. This is the first textbook example of a useful monad in computer science. And what is the notion of a computation here? If you program in a Kleisli category as we do, is a computation gets a stack contents and returns a new stack contents, and then the value of interest, right? So that's what you do. You get stack contents, you return a new stack contents, and then the value of interest drawn from a set x. Yeah, if you do Lagrange theories, or what you call it, then we are interested in what the algebras are for the right theory corresponding to this monad. And they're literally algebras of this monad in the sense of category theory after some simplification. So here, if you do the simplification, you find out that you can work with these two things that I often they're called put and get here. I chose lookup and update, but it's the same thing. So lookup should be something that gives you stack computations. Think of X as some sort of type for stack computations or continuations. And what it does is it takes a dependence of computations on what is on the stack and turns this into a new computation. So maybe the best intuition is here. Lookup F, it reads all of the stack into some list, and it continues as F applied to that list. And then there's the other one for making new computations, of time E star times F to X. So up of ES and X overwrites the stack completely with a given list ES and continues as X, whatever X was. And then you really want that these things hold. So here's a typical one. You do lookup, you get the stack contents, or generally this contents of your storage, and you overwrite the store with these contents, and then you should be able to say, well, nothing happened. At least at some abstraction level, or some level of negligence, some level of don't care. And of two consecutive updates, only the second one should matter in the end of the day. Also, if you update and then look up, then after that you really know what it is that the lookup is going to return to you, so you could use it directly and not do the lookup.
Isn't there also a lookup law?
Oh, there is a big confusion about this. So there can be like 3 to 5 to 7 laws, and it depends on if you're Gordon, Plotkin, or Paul André Méliès, etc., which laws you write. This one is very much inspired by rewriting, and this is something I want to emphasize. So what's the connection between this business here? So if you didn't have, let me just make one remark first, and then go to what I want to say. So if I didn't introduce these equations at all, if I just said these things without any equations are my algebras, the corresponding monad would be this free monad, where computations are kind of stack programs in a very intentional sense. So you see the whole history of what you have been doing in your notion of computation. So it is this inductive data type. The computation is either an immediate return, or some read and then continuing, well, as a computation, or some writing or some putting and then continuing, well, as a computation. Now, for some odd reason, if I impose these equations, which corresponds to quotienting this data type here, I land here. Well, how is this? Where does it come from? And from me, it does come from this. If you think of this as an equational theory, you could even try to look at it as a rewrite system, orienting all these equations to the right. Then there's this idea of normal forms. So in the end, all that the stack computation, or state computation here, ever does, the only thing that matters is the first read, well, and the last write. And so any computation you can expand into a lookup followed by update. This is first some sort of an eta expansion. And then if for some reason in your term 2 consecutive updates appear, then you can compress them into one. If there is ever a lookup after update, you can get rid of it totally. So in the end, you just have a sequence of lookup and update, which is exactly the type here. So this kind of thinking is somewhere behind. This is how we prove these things. It's a logical relation proof at the end, but this is not what I want to talk. Let's do something different. I want to track the net write effect of a stack. So, what can a stack computation do? Well, the way we normally program with a state is with these push and pop operations, but some of these cancel each other out, right? So in the end of the day, we have removed some elements, and we have added some new elements, right? That is all you can do. Maybe you've removed all elements, so you went down to the bottom, and then you pushed all new elements. That's fine. That's a special instance, I think. So I want to view this as follows. I use what Danel and I have called an update monad. This is a general concept where you work with a set of states on one hand, which here is the possible stack contents, which are lists, and then there is a set of updates that you allow to be applied to this state space. Here it's going to be pairs of a number and a list of elements. The number you see is the number of elements to attempt to remove, or to remove, depending on how empty the list is or how much it underflows. You should really see this as number of elements to attempt to remove. And then the list is elements to add. And then there is this notion, I mean, you'll soon find out that this update set has a monoid structure. So there is a notion of a trivial update, which means not writing anything, you don't remove anything, you don't add anything, right? And then there is this idea of composing two consecutive updates. You should think, if you first remove and then add, then remove and add again, you should be able to recast this as a single remove and add. And this is a bit of arithmetic, but it's defined like this. So if I attempt to remove n elements, then add these elements, attempt to remove n prime elements, add these elements, the net effect is this. There's some calculation. So n plus n prime minus the length of ES, this is a truncating minus. And here you basically append these two lists, but you have to do a truncating drop. Moreover, so in the end, I may want to apply an update worked out like this to an actual state of the stack. And this is defined like this. And this is a write action of the monad of the set. And the corresponding monad is defined like this. This is a completely generic definition for an arbitrary set of states, an arbitrary monoid of updates, and the write action of the updates on the states. It's defined like this. I like it a lot. A computation here, what it does, it gets the stack contents and returns an update. So you see what you've done to the stack, but actually the update is not applied. Unless you compose two computations, so which corresponds to applying the multiplication of the monad, in which case, you've started from a state, you produced an update, now you have to continue from some intermediate state and produce a new update, but from where do you get the intermediate state? You have to apply the first update. What is the algebra here? Now I've got a finer structure, so my lookup thing is the same. So lookup of f is something that reads the stack into a list ES and then continues as f of ES. But the other two things are here. So pop x leaves the stack unchanged if the stack is empty, but pops the top element of the stack without reading it otherwise to then continue as x. So it's just it's a pure pop. You don't get the element that you pop. And push is an element, give an element onto the stack and continues as x. Here's the axioms that you want that give you a notion of give you an algebraic theory that corresponds to exactly this monad. I got some questions from the referees that I want to answer now. So someone said these are not the right axioms. There are axioms missing. And I want to say, no, this is exactly the right axioms. So you can imagine what kind of things we want to say. So looking up but not caring about what you looked up, this is the same as not doing anything, right? Two consecutive lookups give the same thing, so you don't need to do it twice. If you pop and then you look up, it's the same as looking up before, but then taking this into account that, well, where the lookup was before, there was one element less, and something similar about push and lookup. And finally, pushing and popping gives x. So now I could ask questions, why not any axiom about pop and push, right? So for example, if I look up, I find out the stack is non-empty, and then I pop, and if I push exactly what I popped, I should get, in some sense, the same computation. But it's not. If I start putting in these axioms, I fall back to the old state monad, because I'm not anymore keeping properly track of how deeply I read. Because, well, any removal and adding can of course be completed to removal all the way down to the bottom of the stack, then compensating, I mean, the extra things that were removed, and then adding, well, the things I wanted to add in the first place. So this is exactly what I don't want to do here, and these are the right actions.
But my question again, Tarmo, here you do have a lookup law.
Lookup is fine.
But you didn't have it for state.
Then it follows. But here you have to have it separate. So a nice and sort of systematic axiomatization for the state. We use lookup, and this trivial lookup. So this follows out of some considerations, but then if you go to these rewriting considerations, you find out, well, a nicer set of axioms is a different one, but they really do achieve the same yet. Give the same notion of algebras. So I find this is quite cool because there is lots of modularity here. So why does everything work very smoothly, and why don't you need to prove many things? Is a state monad doesn't decompose into a reader and a writer monad, but an update monad always does. So what we really have here is the composition of two monads, on the level of composing the underlying functors. One is the usual reader monad, I call it T10 here, and the other one is a pure writer monad, where you just collect these updates of the form, remove, add, remove, add. But there is of course more. So why were my axioms sort of so fine-grained? I mean, why didn't I have an operation for removing a number of elements and adding a number of elements? Is that my monad of updates is put together of smaller things, right? So first of all, this writer monad that does removal and adding is put together from two smaller writer monads. One only does removal, the other only one does adding. And how removal and adding should be combined is explained by a distributive law between these two writer monads. So this is happening here. And then the two smaller writer monads, so one that is a writer monad on the monad of natural numbers, and the other one that is the writer monad for the list for the monad of lists, they are free monads, right? So instead of having an operation for removing similar elements at once, I can have an operation for removing just one element, and everything else can be expressed by iterating that operation, and similarly for adding. So there's a layer of structure here, and you really put everything together from like reading the whole stack, popping a single element, adding a single element. I may also, I mean, this is not quite yet stack computation, right? Because somehow I had the feeling here was that somehow my stack was random access as long as reading was concerned, and then I was very careful about writing, which is maybe not how you normally want to program with a stack, right? So this corresponds now to my second version, 012. So here I also want to track the net read effect. I'd like to really understand what it is I do to a stack if I look at yet closer. And the way you work with a stack is, in the end of the day, what can I have done? I either didn't read at all, I put some elements on the stack, right? Or maybe I read a single element, and depending on how it went, I decided how to go on. It can go in various ways. I can underflow immediately. I mean, I can find out the stack is empty, in which case, well, I can possibly only add some new elements. Or I can actually see one element, a true pop, that doesn't only pop, but also reads an element, and then depending on what that element is, continue somehow. That's what expresses these kind of computations. So read it as an inductive type, right? This mu z thing. So the first case corresponds to saying a computation found by making an attempt to read a single element that the stack was empty, and I only added some elements and returned some value. The second case corresponds to I managed actually to read an element, and then I what is it? Then I produce some values, or I continue recursively as the same. And here is a small choice. I mean, you could also write this, pull this E arrow out to here. It's a minor thing. So this is what a computation does. And it turns out, again, well, this is a pretty complicated monad. If you were to write out the full definition, you have to look at several cases, but nothing very deep happens here. On the level of algebras, it's fairly simple. All my operations now are the following, and these precisely correspond to the monad I showed. There is two operations and two equations. One is push, that's easy to understand. You just push an element and then you continue in some way. The other one has two arguments. So this corresponds to the two cases that you can get when you try to pop. Either you fail, in which case you just continue somehow. This is the first argument of tpop. Where am I here? Yeah. If the stack is empty, the computation tpop xf just continues as x. Else, you actually read and pop the top element, or whatever it happens to be, some element e, and you continue as fe. And then these are the equations. This one is straightforward. Here you have to think. Had you already hit the bottom, and you try to attempt to read again, you will again see you're at the bottom of the stack. And that again actually comes as a compatible composition of two monads. This is a simpler one which never adds any new elements, and then you compose it with the monad that we had for adding new elements, which was the writer monad for the list monad. And then these things are related in some way, right? So the state monad is the most coarse grain, this is the most fine grain. So here there is an idempotent that you can actually split. Here it would be the same, but I haven't put an arrow here, and this has to do with the fact that if I don't know the depth of the stack ahead of time, then I don't know how deep I may need to look. So to have a similar connection between T1 and T2, I would have to change the mu binder somewhere to a new binder to allow for infinite computations. Now before to finish, I just wanted to make a remark to a different direction, which is that this is all a client view of what stack is. I mean, we're saying we're doing stack computations, and we expect that some computations actually achieve the same. This is what the equations tell us. But then there is the other side of the world. We could actually think of implementing the service of a stack. And that can be done. And it turns out that for each of the monads considered, there is a corresponding comonad, and you do not produce it in any ad hoc way, but it's just the comonad that is determined by the co-models of the same theory, for which on the monad side you're interested in the models, not the co-models. So the coalgebras of these comonads, they are stack implementations. I just want to illustrate it a bit.
So I have a maybe dumb question. What is a co-model?
Officially? Very shortly, right? For Lovier theories, a Lovier theory is some category that is an extension of f-op, and then you must have a product preserving functor into set. Here the only difference is you have a functor into set op that would have to preserve coproducts.
Okay.
No, but it's much more easy on the level of examples, because I really didn't want to write any of this down here, because that would only confuse everyone. And I think everybody that has worked on this has now went into the habit of not showing the details. I know Sam Staten writes these papers like this, that it doesn't show the official Lavier theory kind of thing, but just ordinary universal algebra style presentation operations and axioms. Else you just get confused if you refuse to. But it's not complicated. So think of this. This you have seen before. It's Jeremy will recognize it as something as a comonad whose coalgebras are lenses. Or Russell O'Connor made this observation, and actually Ola Sharavska made it in 2007, but in public. So there is this comonad that corresponds to the same Lavier theory as the state monad. The type is this. D of x is lists over E times functions to x from lists over E. What is a coalgebra of such a thing? Well, it has to be a map from x to d0 of x. And then the first thing will correspond to returning the stack contents. So the stack implementation exposes to you the stack contents. The other one is the one that accepts from you the new contents you want to put into the stack or the store, right? And then it continues as a service. I'll show it here. So lookup takes x, returns e star. X you should think of as some black box that somehow contains the stack, but you don't know how. But lookup tells you how to get the stack contents. Update, which is written here in uncurried form, so it doesn't look like coalgebraic, but it really is. It takes this black box thing, and it does the following. So if you supply new stack contents, it goes into a new black box state. Yeah? And it has to satisfy these things, these equations, which are sort of the old equations we had, but you sort of have to read them inside out instead of outside in. And you can play exactly the same game with, for example, the update monad. You can turn it into update comonad. So this is the type. And you will have these operations. So an implementation is able to return to you the stack contents. If you come with an instruction that, well, please get rid of one of the top elements you have, then it does it for you. But you don't see anything. You just know this was done, right? And then you can push. And these things have to be satisfied. So for example, if you push E onto a stack and then pop it from there, then this thing goes back to the same state where it was before, right? Or if you pop an element and then you look up, it's the same as looking up first, but then dropping one element yourself. So previous coalgebras were nothing but ordinary lenses. These are update lenses, and there is a corresponding version also of the last monad, but I will not comment into this. I will make one more comment. This is my one but the last slide. So how are the two things related? I mean, if I've got this idea of having stack computations on the client side, and then some actually service that provides the stack operations for me, the intuitive idea is that I should somehow be able to, to run them in parallel and have one talk to the other. So what does it really mean formally? It means the following thing. So for any of these comonads I showed, which are stack implementations, right? A coalgebra gives you a monad morphism between the corresponding monad and then the state monad for the carrier of the coalgebra. And that, I would say, is nothing else than the run state function of Haskell, for example, or any run you would want to write for such monad. So just look at this type here. So if you have got a stack computation, or maybe a state computation for simplicity, any state computation, then what the run does, all it needs is the initial value of the state, and you somehow work your way to the final value of the state, right? And then you have your return value. So intuitively, such a monad morphism tells us how to run computations. So there is a connection between any of the monads we look at, and then the standard state monad for these characters. So a take-home message, not just random access store, but intentional aspects of different specific types of store. You can do stacks, you can do buffers of various sorts, so queues, what do you want, LIFO, FIFO, whatever. They can usefully be expressed with monads and comonads. There is often lots of mathematical structure, which means you don't have to prove properties about these things, but you can pull this off-the-shelf small lemmata from the category theory bookshelf. And it's also useful to pay attention to comonads here. So comonad coalgebras, they provide implementations for these different types of stores. That's all I wanted to say.
So we have time for a couple of questions.
So are you familiar with Peter Hancock's and Irenat's paper, Programming Interfaces and Basic Topology?
Programming interfaces and?
Basic and formal topology.
No.
If you go back to your co-state thing, you know, it looks very much like a non-dependent container. So the position set doesn't stand.
Sure.
Yeah,
that I know very well.
And then there is, they have a general result about, like you say, then kind of, you have the client side, which is the free monad of a signature, in some sense. And then the co-interpretation of the co-free co-monad of the co-interpretation.
I should look there. Yeah.
So they have this result saying that, yeah, you can combine these two and get, just like you said, one of them is a client, one of them is a server, and you can combine them and get the result. It seems to remind me about this.
Yeah.
But more generally, not for a specific, state, but rather a general signature, any kind of container.
Well, indeed, these co-state comonads, they are, I would say they are a special case of directed containers. So it's containers with extra structure, not just the functor, but the comonad. Right? You can be a lot more precise there, going dependently type theory.
Another question?
So when you model so you track only write facts, right? And you have this E star, so do you attempt to predict which elements will be written to the stack? Despite you don't know what was in the stack, and like your computation can read from the stack, and based on that decide what to write to the stack. Exactly. But it seemed like you have a specific E star in mind that you expect to be written to the stack. Or did I misunderstand it?
So here.
Right.
So computation is something in this type, right? All that it is a function that gets a list, which you should think of as the current stack contents.
Oh.
Right? And then it produces three things. A number, which is the number of elements it tries to remove. So it may actually remove less if the stack is shallower. And some specific elements to add. So and the value of interest.
Yeah,
so if in the end you were to apply, so literally you remove this number of elements from this initial state of the stack, and then you add those.
Yeah, I mean, until you know the exact initial contents of the stack, you cannot tell anything about your computation in this stack system, right? So if you just look at the computation without knowing what the input will be,
Sure.
You cannot tell anything about what will happen.
No, I mean, if you want to see it as, I don't know, some sort of, if you would want to use this as some sort of analysis, kind of static analysis, like, I mean, these effects they're really functional dependencies still, right? It's not that I predict some upper bound on the number of elements to remove that doesn't depend on the stack content was at all. So there is clearly a relation to this indexed monads business, for example, by what's the name of the Japanese brand? Shinya Katsumata. But what we're doing is different, right? So there you try. you've got a simple simple monad like state maybe to do these stack things, and then there is indexed versions of them, which are not even monads, but somehow is if you look at it sort of as collectively, this is a similar concept, and then you can do a static analysis, but one and the same computation can belong to different approximating types, right? Here it's not like this. But there is, of course, a clear relation between the two approaches. So here there is a single type into which you have to fit.
Can you ask about Quark sets up?
Yeah. So I have a question. The common theme here is, if I'm correct, is that you say I have these operations on stacks which I want to capture, and I want to interpret them in this monad, keeping track of read or write effects or what have you. And to do that, I need to take the term algebra and quotient through these equations. How do you find the equations?
Depending on where you start, right?
Yeah. So if you say I have this term algebra, I have this monad that I want to interpret it in, and then what you said is, oh, and these are the equations I need to quotient by in order to get this semantics that I need.
Well, there is a general method for doing this, but it doesn't give you anything very useful. So you have to do sort of ad hoc simplification afterwards, right?
Yeah.
Which is pretty creative.
Yeah.
But I think very often you start at the other end. You know the operations, you know the equations you don't want to enforce.
Yeah.
Then you want to work out what is the simplest way to say the monad.
Yeah. What is the monad? Okay.
Like as I explained for the state case, right? I mean, you know the lookup update. You have some idea about equations. Now, why should the type of the state monad be like this? Because the normal forms are that, which is somehow figured out, right?
Okay, but is there a principled way to figure out, or is it that you kind of stare at it and fiddle around a bit and this thing matches?
I think we should take it offline.
Okay, yeah, that's fine.
Well, how do you choose the right monad is another kind of related question.
Yeah.
It's the same kind of concept. Okay, thank you. Yeah, we should. There's lots of things to ask, but we should really carry on. Thank you. It will be entangled state and bidirectional transformations and other effective stories, right?
That's right.
And
Yes.
what? Yeah, example.
Hi. Today I'm going to talk about computational effects as well. In particular, combinations of computational effects. So with a leading example arising from bidirectional transformation, which is something I'll explain a bit about. So entangled state is something that arises from bidirectional transformation. And along the way I'll also talk about some other effectful stories, which hopefully will give me some ideas about how to tackle this problem. It's very much work in progress. It's stuff I've been looking at as part of my PhD with Jeremy. Okay, so let's deconstruct what I mean by separating entangled state, starting with the word state. So what I mean by state, I mean the state monad, which you'll be familiar with. Let's say, by the way, so in this talk I've used sort of pseudo-Haskell, pseudo-mathematical notation, but I mean it should be hopefully understandable. So for the state monad, you'll see that it's basically a state transforming function, and it emits whatever underlying value. Of course, there's also more to it than that. There's a return and there's a bind as well. So there's three parts to the monad. And as you would know from the first talk of the session, we know that a monad can be presented in as part of as an algebraic theory. So so you taking the view of the state monad as a single mutable state, we have a pair of algebraic operations, get and put, which can be read as follows. So the get is basically like a lookup on the state, and the put will overwrite the state with an updated state. So the M stands for the monads. I mean, these are quasi errors, so these are actually generic effects rather than algebraic operations, strictly speaking. If you're familiar with plug-in Powell's work. You can think of these laws as so you can think of this algebraic theory as an interface, if you will. So what property should a monad satisfy to implement this statey behavior? We should have these operations, and these operations get and push to satisfy these laws as well. For example, for the first law, we have a law stating that if we write S to the state and then follow that up with another write S prime, then well, that's the same as just doing the second one because the first one is overwritten. In the second instance, if we write to the state with the variable S and then immediately look it up, then well, surely it's what's looked up is the S that we put in. Similarly, if we look up a state, whatever we get, we write it back in. Well, that's like doing nothing. And if we look up the state and then follow it up immediately with another lookup, followed by some computation k, that's the same as just a single lookup and running this computation with the first lookup, because the second lookup would have been the same. So, so I think one of my referees said one of these laws is redundant. That's probably perhaps the case. I don't know, but I've chosen to present them this way, and this is how it's usually presented, at least to Haskell programmers. So we know what state means. So how to motivate entangled state? Well, it's something that arises from this idea of bidirectional transformation. And the basic idea of this is essentially to keep two information sources in sync and consistent with each other. So the classic example is you have a database containing your master data, and then there'll be a view on this data. And then in your view, you might want to make some changes, and then the problem, if you like, is then to update the database and keeping it consistent with the changes you've made in the view. So this is, this general sort of single view and a model bidirectional transformation we call view model BX. BX is short for bidirectional transformation. This can be studied more abstractly, in terms of a pair of functions lookup and an update, which Tarmo mentioned, and it's called lenses, although I won't talk about that so much in this talk. Okay, so with a view model BX. So I said, there's you can imagine a mental picture of a database and a view, and there are sort of two operations that you can that are sort of going on here. So, so as I said, you take a view from the model, which is your database, if you like, and you can. And then later on, you might make some changes to the view, and then you want to sort of sync your database with your data view. So that's like a view and an update operation. So that suggests, the state monad to be a good candidate to implement this kind of idea. So we have a view and an update operation, and they have the same type, as the get and the put operations. Although it's worth noting that the M is the same M as before. So So for view, for example, this is a state as v. Update. So v to a state. Sorry,
The tree.
Please write bigger.
Oh, okay, sorry. This is update. Okay, I mean, all I'm doing here is just reminding you that M is the same state monad as before, so the M is the state S. So what I want to highlight here really is there's two variables here, S and V, and the V represents a view and the S the model. So there's the view and the model are distinct here. Now they satisfy the same sort of analogous laws as the state monad. So the get, the get put, and so forth. But curiously, not the put law. So that's the first one here.
Sorry, this may be a dumb question, but why does it have to satisfy the get put law? Because I don't know. I mean, like I'm just thinking of incrementing a counter and viewing it, or is that a bad example?
I mean, these laws sort of fall out from the algebraic theory of global state, and these are kind of rephrased for the case when there's just one location in the global state. So, I mean, if you like these laws,
so those laws make sense. But you said for the views, you get the same laws, but not.
Not the first one, yeah.
Yeah, but not the first one. And if the first one fails, why does the third one?
So the expectation is that when you put, when you update, you have to synchronize your view with the state, and it's a consequence of retaining this get put law. That if the view that you're synchronizing is already consistent with that state, then nothing can change.
Okay, so it's a choice you've made.
It's a choice you've made. Yes, it doesn't. It doesn't follow from anything that Paul said already.
Okay.
Sorry, I have more question. Simple. View is a common word.
It's a common word.
It's a general word. Is a monad or put and get is a common very for me. But view is first here.
Oh, okay. So it's a sort of database terminology. So you have a database and you might take a view on this.
First of all, it's a common word.
Well, it's common in if you've seen it before, I guess.
If you go to different communities.
Think about a projection and the selection out of a database table.
Right.
Okay, I understood what I will thanks a lot.
So okay, so why should it not satisfy a put law? Well, let's take the example of let's say your updates, as well as writing something. It also updates a log. Imagine there's some sort of logging context in there. So I mean, I do a first write thereby updating the log to say I've written an S, and then a second one to say I've written also an S prime in there. I mean, clearly there's no reason why we should expect the first one to be discarded. I mean, there's a dependence here on the history, because we've written it in here, we can't say we can't just throw it away. So that's a very simple example.
So do you expect some form of commutativity log for update, like update V followed by update V prime, same as the other way around?
So no. No, we don't. Yeah. So I mean, that's what precisely what I'm saying by this law. Yeah. That they should not commute. But we'll talk more about commutativity. Yeah. Okay. So in a general BX setting, we might want to have more than one view on the model. Why might we want that? Well, in so-called model-driven development, you may have one, you would have one sort of single collection of all the master data, and then you'd have different perspectives, on this data. So, in a kind of a UML setting, you'd have, in fact, class diagrams as being one perspective on some data, and another perspective would be sequence diagrams. So one